Okay, so once again, welcome back to another lecture video. So for today's lesson or for today's lecture video is we will be discussing all about the second law of thermodynamics. So for the outline of this topic that we will be discussing today, first again is we will be discussing all about the second law of thermodynamics, as well as we have the heat engines. So we will discuss Otto cycles, we have the diesel cycles, as well as the Carnot cycles. And also, not only the heat engines, but also we have the refrigerators. Alright, so let's start. So now, when we will define the second law of thermodynamics, so the second law of thermodynamics can be stated in several equivalent ways. Now, number one, we can state that in Kelvin-Planck statement, in which it states that no heat engine can convert all absorbed heat into work. So some energy is always lost to a cooler reservoir. Okay, so that is Kelvin-Planck statement. Second law of thermodynamics that is stated to Kelvin-Planck. Now the second one is we have the Clausius statement. So according to Clausius statement, heat cannot spontaneously flow from a colder body to a hotter body without the work input. And the third one, we have the entropy statement. So see, entropy statement states that in any thermodynamic process, the total entropy of an isolated system can never decrease. So it's either it increases or it remains constant. So this law, or the second law of thermodynamics, it implies that the perfectly efficient machines, which we also call as the perpetual motion machines of the second kind, are impossible. Okay, now let's go to the heat engines. So if we will define a heat engine, so heat engine is a device that converts thermal energy into mechanical work by operating in what we call the cyclic process. Okay, so we have, again, as we have mentioned in the outline, we have the Otto cycle, we have the diesel cycle, as well as we have the Carnot cycle. So let's discuss that one by one. Now, let's proceed to the Otto cycle. So let's start with the Otto cycle first. Now, the Otto cycle is used in spark ignition internal combustion engines. So, for example, we have the petrol cars. Okay, now on the right side of this presentation is we have the PV diagram on what is happening on the Otto cycle. So we have four processes. Number one is we have the adiabatic compression. So this one right here. So nadiri nakatudlo sa arrow. So adiabatic compression. So this is from point A to point B. So here, that's one, point A to point B. So what happens here is the air-fuel mixture is compressed. So there is no heat exchange. So therefore, the temperature and the pressure will rise during this compression or adiabatic compression, or what we call the compression stroke. Now for the second one, number two, we have heating at constant volume or isochoric heat addition. So what happens here is, so this is from 2 to 3. What happens here is the spark ignites the mixture and the rapid heat release. So what we call the fuel combustion. So the volume is constant. So also the pressure rises sharply. Now from 3 to 4, so from 3 to 4, what happens is it is an adiabatic expansion, or what we call the power stroke. So what happens here is the gas expands and does work on the piston. So again, there is no heat exchange and the temperature and the pressure drops. And then fourth one is from 4 to 1. What happens here is an isochoric heat rejection, or the cooling at constant volume, or the cooling of exhaust gases. So the exhaust valve opens and also the heat is rejected at constant volume. So that's why it's called isochoric heat rejection. And also the pressure drops. Okay, so those are the 4 processes. Again, number 1, we have the adiabatic compression. Number 2, we have the isochoric heat addition, or the constant volume heat addition. And then we have the third one, which is from 3 to 4. Number 3 to 4 is the adiabatic expansion, or the power stroke. And then the fourth one is the isochoric heat rejection. Okay, so that is the overview. So by the way, the cycle moves, if you have noticed, the cycle moves in a clockwise direction. So clockwise direction, indicating the net work output. Okay, so that is Otto cycle, or what we also known as the gasoline engine. Okay, now if we want to solve for the efficiency of the Otto cycle, we have here efficiency of the Otto is equal to 1 minus 1 over R to the gamma minus 1. So our R is the compression ratio, which is equal to V1 over V2. And our gamma is the heat capacity ratio. Okay, so the heat capacity ratio is equal to Cp over Cv. Okay, so that is how we would solve the efficiency of a gasoline engine or sa Otto cycle. Okay, now let's have the second one. So what happens here is we have the diesel cycle. Okay, so sa diesel cycle, or it is also known as the compression ignition engine. So obviously from the word diesel, so it is used in diesel engines. Okay, so also pareha kay Otto cycle, si diesel cycle also has 4 processes. Okay, so number 1, first one is the adiabatic compression. Okay, so adiabatic compression, this is from point 1 to point 2, or from 1 to 2. So adiabatic compression or compression stroke. So what happens here is the air is compressed to high pressure and temperature. So there is no heat exchange, and then the fuel is injected. Now, the second process is what we call the isobaric or the constant pressure heat addition. This is from 2 to 3. So number 2 to 3 processes 2 to 3. So what happens here is the fuel burns as it is injected. So the volume increases while the pressure remains constant. And also, this is the time that the temperature will increase. Okay, now after that, we have the adiabatic expansion. So from 3 to 4, from processes 3 to 4 is the adiabatic expansion or the power stroke. So what happens here is that the combustion gases expand. So again, no work. There is work on the piston. There is work done on the piston and no heat exchange. Okay, so that is the third process. Now the fourth one is from processes 4 to 1, which is the isochoric. The fourth process, isochoric heat rejection. So what happens here is that the exhaust gases are now expelled, and also heat is removed at constant volume, and then the pressure drops. Okay, so those are the 4 processes on what is happening by looking at the PV diagram of a diesel cycle. That is what happens during a diesel cycle nga engine, or mo na yung nagkakahitabo sa diesel nga, or the compression ignition engine. Okay, so again, it has also 4 processes like the Otto cycle. Now, as for the efficiency, ang formula to solve for the efficiency of the diesel, we have 1 over R over 1 minus 1 over R to the gamma minus 1, and then times, we have rho. Our rho here is the cutoff ratio. So rho to the gamma minus 1 divided by gamma times rho minus 1. So that is how we would solve for the efficiency of a compression ignition engine. Okay. Now, we have the third one, which is the Carnot engine. So, si Carnot engine is a theoretical thermodynamic cycle that is proposed by Leonard Carnot. So, it estimates the maximum possible efficiency that a heat engine during the conversion process of heat into work and conversely working between two reservoirs can possess. Okay, so the same with Otto and diesel cycle, si Carnot engine or Carnot cycle has also 4 processes. Okay, so let's discuss those processes. So, by the way, before we proceed, Carnot cycle is defined as an ideal reversible closed thermodynamic cycle in which there are 4 successive operations involved. Okay, so it consists of two isothermal and 2 adiabatic processes. Okay, so we will explain that later on, each of the processes. And also it operates between 2 reservoirs, T sub H or at the hot temperature and T sub C, which is the cold temperature. Okay, so si Carnot cycle is also known as the ideal or the theoretical na engine. So, ang purpose ni Carnot cycle is it represents the maximum theoretical efficiency of a heat engine that can achieve between 2 thermal reservoir, which is the hot and the cold nga reservoir. Okay. Now, to solve for the efficiency of a Carnot cycle, we have efficiency of Carnot is equal to 1 minus Tc over Th or T sub C over T sub H, or the cold na reservoir divided by the hot na reservoir. Okay, now let's explain what happens here on our PV diagram sa Carnot cycle. So, as you can see on the figure in the right side, so we have 4 processes again. Now, let's start with the first one. So, again, clockwise gihapon ang direction sa ato ang processes. Okay. So, number 1, what happens here is what we call the isothermal expansion. So, sa isothermal expansion, which is at high temperature, so the heat is absorbed from the hot nga reservoir, and then after that, the gas expands and does work on the surroundings. So, but the temperature remains constant. So, if we want to solve for the delta U or the internal energy of the system, it is equal to 0. So, meaning that the heat absorbed is just equal to the work done on the surroundings. Okay, so that is a Carnot cycle. Number 1, first na process sa Carnot cycle. Okay, now let's go to the second one, or in B. Okay, so in the second one, we have here the adiabatic expansion. So, number 2, kani si adiabatic expansion. So, what happens in the adiabatic expansion is that there is no heat exchange, or Q is equal to 0. So, also, the gas continues to expand and cools to T sub C, or our cold nga reservoir. And then, the work is done by the gas. So, work is greater than 0. So, if we want to get the change in the internal energy of the system, it is equal to the negative work. So, okay, since Q is equal to 0, so our internal energy, change in internal energy is equal to negative work. Okay, so that's number 2. Now, the third process from C to D is, what happens here is there is an isothermal compression at low temperature. So, ang mahitabo na diri is that the heat is released to the cold reservoir. And then, the gas is now compressed and the temperature remains constant. So, since in this case, or what happens in this process is that the change in internal energy is equal to 0. So, see, heat is equal to the negative of work, or work is less than 0, which is negative. Okay, so that is the third process. Now, the fourth one is we have the adiabatic compression. So, from D to A, point D to point A. So, adiabatic compression ang kakahitabo diri sa fourth nga process or sa last na process. So, in this process, there is no heat exchange and the gas is compressed and its temperature rises from the cold to hot nga reservoir. So, there is work done on the gas. So, that is the 4 processes on the Carnot cycle. So, I hope you remember that one. So, each of the processes sa Carnot cycle, sa Otto cycle, as well as on the diesel cycle. Now, let's discuss the refrigerators and heat pumps. So, both devices, or both of these devices, transfer heat from a cold reservoir to a hot reservoir. So, but they do so for different purposes. So, we will differentiate refrigerator and heat pump. So, ang purpose ng refrigerator is to keep a region cold by removing heat from it. Whereas, si heat pump is it warms a space by pumping heat into it from the outside. So, muna yung mga purposes between a refrigerator and a heat pump. So, again, both of these devices transfer heat from cold to hot nga reservoir, pero lahi-lahi ang ilaang purposes. Okay, so what happens here? What is their thermodynamic cycle? So number 1, the first one is evaporation. So low pressure and low temperature. So mag-start ta diri sa evaporator. So the refrigerant absorbs heat from the cold space or the evaporator. So it vaporizes from liquid to gas. What happens next is we have the compression. So padulong siya sa compressor. So the gas is now compressed using a compressor and the temperature and the pressure will increase. So there is work done on the refrigerant. So after the compression is maabot na po siya diri sa ato ang condenser, or what will happen here is there is a condensation. So, there is high pressure and high temperature. So, now the hot refrigerant releases heat to the warm surroundings or to the condenser. So, it condenses na dayon from gas to liquid. And then, the last one is the expansion valve or the expansion device. So, the pressure after this one, pag abot diri sa to expansion device, the pressure and temperature will drop suddenly and the refrigerant re-enters again the evaporator to repeat the cycle. So, balik-balik lang dahil ang cycle. Okay. So, again, those are the thermodynamic cycle. First one, starting from the evaporator, there is an evaporation. And then, next, we have the compression. After the compression, we have the condensation. And then, we have the expansion valve or the expansion device na dayon. Okay. Now, okay, so na-explain na diri. We have on the next slide what happens during or the thermodynamic cycle of refrigerators and heat pumps. Okay, now let's go to the applications. So, going back to the 3 types of heat engines. Number 1, we have the Otto cycle or the spark ignition engines. So, ang application niya is gasoline cars, we have the motorcycles, we have the small boats, and also portable generators. So, mostly sa gasoline cars, most passenger vehicles use Otto cycle engines. And also for the motorcycles, the lightweight 2 and 4-stroke engines follow the Otto nga cycle nga behavior. And for the small boats, we have the outboard gasoline engines. And for the portable generators, it is used for short-term power in residential or remote settings. So those are the application for Otto cycle. Now as for the diesel cycle or the compression ignition engines, we have the trucks and buses. So there is high torque and efficiency make diesel ideal for heavy transport. So as you can see, or if you have noticed, ang mga trucks and buses uses diesel nga gasolina. Okay. So most, or I think all of the trucks and buses kanang mga dagko nga sakyanan, they uses diesel para itubil sa mga trucks and buses. Okay. Because again, ang trucks and buses use the compression ignition nga engines. Okay. So we also have trains. So the trains use diesel electric hybrid systems, and also as well as the agricultural machinery. So we have the tractors, the harvesters due to ruggedness and fuel efficiency. So another one, we have the ships and marine engines. So description for this one is they are reliable and long distance fuel economy, and also industrial generators. So backup and continuous power supply for the factories, the hospitals, etc. Okay, so gagamit na sila og compression ignition na engines. Okay, now the third one, we have the Carnot cycle. So sa Carnot cycle, since it is a theoretical ideal engine, so ang application niya is thermodynamic benchmarking. So it is used only in textbooks and theory to compare real engine efficiency. And also, they are used in cryogenics and physics research. So sometimes idealized in analysis of experimental thermal machines. So gibutang dere nga no real-world engine operates on a Carnot cycle due to practical limitations. Okay, again, Carnot cycle is also known as theoretical ideal engine. Okay, so for the refrigeration and heat pumps, application for the refrigerator, we have the household refrigerators or freezers, kanang nasa tong balay. We have the laboratory equipments. Also, we have the refrigerated trucks and cold chain for vaccines. As for the number 2, air conditioner, which is also a type of refrigerator. So application niya, we have the residential cooling, kanang mga air conditioners sa atong balay. We have wall units, split type, and central AC systems. We also have kaning sa commercial buildings or even sa schools and so on. And also sa vehicle nga air conditioner. So it is found in cars, buses, trucks for passenger comfort. And then for the heat pump, application na to is the home heating systems. So in the Philippines, dili kay siya common ang home heating system. So mostly in the US or sa katong mga countries nga naay winter nga season. And then we also have the geothermal heat pumps. So use underground temperatures for highly efficient heating or cooling. And also the eco-friendly climate control. So it is widely used in energy efficient homes and also green buildings. So that's it for our discussion. So again, we've discussed the second law of thermodynamics, the different types of heat engines, and also the cycles. And also, we have the refrigerators and heat pumps, as well as their different na applications. So I hope you've learned a lot from our discussion today. And I think we'll see you on our next lecture video discussion. Thank you so much for listening. Bye-bye.